Hi class. All right, this is 16.2, part 2, and we had just left off on example 3, so we'll be finishing that one. It says if triangle DEF is congruent to triangle JKL, and DE is 18, EF is 23, and DF is 9x minus 23, JL is 7x minus 11, JK is 3y minus 21, find the values of x and y. So we're given a bunch of side expressions for side measures. First thing I would do is create my triangles. So I would just draw two triangles and make it as easy as possible, keep everything lined up so it's just slid over. Label this DEF, and then label the second one JKL, just because that's the easiest way to go. You have D lined up with J, you have E lined up with K, and you have F lined up with L, just like it is in the congruency statement. Once those are lined up properly, then you can start, DE is 18, you can start marking these. EF is 23. All right, DF, and you just find them, write them in, is 9x minus 23. JL is right here, and it's 7x minus 11. JK, right here, is 3y minus 21. All right, so once you've labeled them all, another thing you can do that might help you out a little is to color code or mark the sides that are congruent. DE, first and second position, JK, first and second position of the congruent statement, so I know those are congruent. All right, also, let's see, EF, second and third, so it's going to be congruent to KL, second and third. And then lastly, we have DF, and it's going to be congruent to JL. So if you mark those appropriately, then you can see which sides are congruent to which sides. I'm going to hit color coding, kind of helps visually, but then generally you don't get that on notes. What you're going to actually get are just dashes, so I want you to be familiar with both of those. All right, so to find x, we need to come up with two congruent parts that have x's in them. And we have that right here. Our marked 3 dashes. We have 9x minus 23 is 7x minus 11. So in order to find x, we can set those two equal to each other because they are corresponding parts on congruent triangles. All right, so you can solve that. Subtract 7x from both sides. And then you get 2x, that's not an x, 2x minus 23. And that's equal to negative 11. All right, and then add 23 to both sides, you get 2x equals 34, so x is 17. And then to find y, we need an expression with y in it. The only y I have is jk, it has a 3y minus 21, and it belongs to DE, which is 18. So 3y minus 21 is equal to 18, is our expression, or our equation we'll write up and solve for y. And add 21, you get 3y is 39, and then divide by 3, and you get y is 13. And there we've done it. Okay, so the next part is asking us to figure out little shortcuts for triangles. Now, so far, we have congruent triangles with 6 corresponding parts that are congruent. Now, what we're going to be working on is proving these triangles are congruent, which is a little tricky. In proving the triangles are congruent, as we see right now, we see 6 parts that are congruent. We have 3 different sides that are corresponding and congruent, and 3 different angles that are corresponding and congruent. With that, luckily, we've come up with some little shortcuts, and I'm going to show you the shortcuts right now. All right, shortcuts are helpful because they show us that or prove that 2 triangles are congruent, even when we haven't proven all 6 parts, which is going to be a very difficult thing if we're trying to prove all 3 sides are congruent and all 3 angles are congruent. Normally we can't do that, but what we have here are we have 3 different pairs of sides of triangles, and we're going to call them corresponding parts to sides. So we have these 2 that are the same length, these 2 that are the same length, and these 2 that are the same length. All right, so with them, I'm going to create a triangle. Now, one triangle, if I have a side, side, side triangle, okay, like this, side, side, side. probably going to need a little longer side, aren't I? I guess it comes together all right. Okay, so this is one triangle, and I have this side I know is congruent to this side. This side is congruent to this side, and this side is congruent to this side. So I have three corresponding sides now that are the same measure. Now, can I build another triangle that looks different than that with these three sides? Or if I have all three sides the same measure as all three sides, is that a good shortcut? Do I need to even prove the angles? Because I can make more than one triangle. And the answer is no. If I set these up, even if I flip it or rotate it or do anything, I can't set them up to touch each side without having being a congruent triangle to the first one, because all the side measures are the same. So this triangle and this triangle will be congruent even though they flipped and rotated, because these sides are the same, these sides are the same, and these sides are the same. There's no other way to put together the triangle other than to have it congruent. So side by side is one of those shortcut methods to prove two triangles are congruent, even though I don't have to prove all 6 items. And that makes it a shortcut. I only have to prove that all the sides are the same. I can't come up with a new triangle if I have 2 sets of the same sides. All right, so the next one, what happens if I get rid of this part and I have a side, an angle, and a side the same as a side, angle, side? So this angle right here is going to be the same measure as this angle. So I can only set this up so that I have that same exact angle. And when I set this part in, then it creates that specific triangle. Now, if I only have a side, angle, side here, and we kind of go around in a circle here, we have side, angle, side. So we'll call it side, angle, side. And notice that this angle is included. It's between, it's not either of the other 2 angles. It's the angle that's between the 2 sides. If I only have that, can I do anything with this? With the same setup, the same side measure, the same angle measure, the same side measure, can I make a new triangle at all? Or am I tied to the same exact triangle with that side, angle, side being the same? And the answer is I'm tied to the same triangle. I cannot come up with another triangle. I can only just connect the 2 sides with a side that will be the exact same measure, creating the exact same angle measures on either side of it. And I have 2 congruent triangles as long as I know this setup side, angle, side. We call it side, angle, side. All right? Only way we can do it. Now, if I take this triangle and I have the opposite, and this is going to be kind of crazy right here, I have to keep this angle the same. Like I can't move this out and make any different angle. If I keep this angle exactly what it is, this side measure exactly what it is, and this angle measure here exactly what it is, then if these angles are stagnant, there's no other side measures that can come together. I mean, they're going to come together and they're going to meet at that point right there, and that's going to finish off the triangle no matter what, because this side measure is set and these 2 angles are set. I can't move this angle to anything different, and I can't change this angle to anything different. So I have to have side measure and 2 angles where my 2 sides are going to come together at a specific part anytime. Now, that means if I have this side the same as this side, okay, and I have my 2 angles coming off the edges of them that have to be a specific angle measure, very specific. This one has to be the same as this one, same exact angle measure, and this has to be the same exact angle measure as this. Are these going to come together at any point other than making where they would make the same exact triangle? And the answer is no, they won't. So angle, this is angle, side, angle as I go across. An angle, an included side, and an angle. All right, angle, and then an included side, and then an angle. Notice the side has to be the one in between the 2 angles in order for angle, side, angle to work. But angle, side, angle is one of those shortcut methods as a way to prove triangles are congruent. All right. Now we have a couple more shortcuts that will only generate the same exact angle if we're given these exact measures. And it is going to be not this side. It's going to be kind of weird to write this up, but I have the two angles already. Angle, angle, and then side. All right. So if I have this angle is specific, whatever it is, 30 degrees or whatever, and this angle, whatever it is, 20 degrees. If I have those two angles the exact same, and then I have just this side that's the same exact measure, so angle, angle, side. So if I have to put something in there to create a specific angle, and I have to put something in there to create a specific angle, with this side being stagnant, then there's only one way to connect right there to make this side match up to the vertex of this side. So can I build it any other way? If I have this side measure that has to be the same, I can only move this to that same exact angle that's right there. So whatever that is, I measure that the same. And I have to make sure that I put this together right here at a certain angle. I move it at a certain angle, then it's going to just match up perfectly with that right there, and it's going to make the exact same triangle. And as we go around, we go angle, angle, and then a side. This side is not included between the two angles, it's outside, so we write that way in our statement, in our theorem. It's angle first, then an angle, and then a side. And that's our second to last shortcut method. And we actually have one more, and it is going to be specific to a right angle. So it's a triangle with a right angle. And I think with my pieces I have right here, I don't think I can actually make a right angle because this is going to be obtuse and I have kind of funny parts. But I'll see if I can do it with these. I'm not sure. Or maybe I'll cut these in half. It's kind of funny how sides and measures have to be the same. All right, I can't use my big long ones when I'm dealing with the rights. Okay, so if I have these three sides that are made specifically to what they are, and then if I take and make a right angle, let me see if I can actually do it with these. I don't know. I have to maybe cut this down a little bit. I guess that works. Kind of, we're all used to using our imagination with Mrs. Juliana's little artwork, right? Okay, so if I have a right angle right here, so it has to be a right angle. That can't be anything other than a right angle. And then I have this leg the same, one leg, and it doesn't really matter which one, and this hypotenuse the same measure. Okay, I'm not talking about any other angles other than a 90-degree angle right here. I have to put this to a 90-degree angle. The only thing I can put there is that side measure right there. So with a right angle, a leg, and a hypotenuse, then can I build anything else? So I have to have a right angle to create a right angle, right? I have to create a right angle, and this has to be a specific, the same measure as that. And then this hypotenuse has to be the same measure as the other hypotenuse. Is there anything, any other way to create this triangle without this being the same and my two angles being the same? And the answer is no. And that is the third way to show triangles are congruent, the third shortcut, and we call it HL because it's a hypotenuse and a leg that have to be the two sides, and then the right angle, and that's the only right angle one. Okay? So those are my shortcut methods, and stay tuned for part 3.